Bene, buongiorno. No, qui non c'è modo di sapere se siamo tutti o no, ma essendo le 11:15 si partirà dall'ipotesi che siamo tutti. Enrica, te cosa dici?
Ma io sarei svizzera in questo senso.
Va bene. Ricominciamo allora. Tanto la registrazione ho visto che continua a andare. Non so se l'avevi fermata.
No, perché non voglio rischiare.
Va bene.
Sì, potete fare la manina con la thumb up, se ci siete. Bravi. C'è una mano alzata addirittura, Nicoletta.
Nicoletta.
2 mani alzate.
Luca.
Lucia.
Ah, Lucia, Luca, era giusto, è Lucia.
The hands on, it means you want to speak or you are present.
Lucia, you have your hands on, means that you are present or you want to say something.
I'm present.
Lucia ha abbassato la mano, quindi voleva solo dire che era presente. Okay. We will switch to English. Alice is looking at us. You're back here. Okay, again, now I will try to skip something because I want to arrive to some good points, but stop me if there is really something that you miss, but not the details. What I'm trying to convey is the big picture. Again, what we have seen now, the text. What is important is to understand that inside the computer, the text are numbers. And what you have to tell the computer is which table you are using to make the correspondence between the numbers and the actual character that it is meant for. And as of today, the most commonly used table is UTF-8. So this is the basic notion. So the documents, now we again, once that you have the text, you can arrange the text in many different documents, in many different ways, so to speak. And so the documents, the most simple ones are to use the Windows notation are the TXT files, in which the text is really a string of characters. And let me, so to speak, the only information about the format is the carriage return, meaning when you want to move to a new line. Here, of course, the standards, as I keep saying, are good because there are many, so you can choose. But for example, Windows and Apple Mac represent the new line in two different ways. Meaning Windows is following the tradition, which is that the new line is two characters. One is the line feed, meaning moving to a new line, and then the carriage return, meaning the moving the printing head at the beginning of the line in Latin alphabet at the extreme left, in Hebrew or Arabic on the extreme right. And this has to do with the origins. I mean, when the printing device were teletypes or things like typewriters, in which in order to move to a new line, you not only have to move to the line below, but you also had to bring the printing head back to the beginning of the line. Apple that started in more recent time, meaning as you have seen in the 80s, they've decided that one character was enough, so they use only line feed to say that there is a new line. But in any case, so this is the plain text. There is no format information. Then there is another family of document formats, which is the family of PDF, portable document formats, which is basically starts, we see that in a moment, but basically they try to represent the way that the text will be printed. So they are basically, this is essentially Postscript. There is no, the formatting information is embedded in the way that the document will be printed. And then there are what are called the text editors that are very often called word processor, because they instead must have two kinds of functionality. One functionality is the editing of the contents, meaning that you want to find the words, to replace word, to change something. So what you are doing with the functions of the editing of the contents is dealing with the textual content, regardless of the format. Why the format is what? I mean, then, however, it should be clear that as long as it is inside the computer, the text is a long string of characters, or now that we know better, is a long string of bytes, zeros and ones. This is how it is inside the computers. But clearly that is of no use for a human. So you want to output, to make available this text. And at this point, you have to tell the system how you want it formatted, whether on a printed page or on a screen. You have to tell the system when it is the moment to move to a new line, to move to a new page, whether the next 5 words have to be in red, or maybe they have to be in bold, and so on. So let me say, you have to provide to the to the text editor also the information about formatting. And this we will see better in a moment. This way in which you provide information about the formatting is either with markup languages, meaning that you embed in the text also instructions about formatting, so that in the end, if you look at how the document is internally, you see a long string of characters where some of them is the text that will be printed or displayed on a screen, and some of them are the commands just telling those instructions. Instead, the other one is the new generation of editors that came out with the screens and the mouse. They are called Wysiwyg, which means what you see is what you get, meaning that you don't have any idea on how the system is keeping this information, because you interact with the editor just on the screen, and you click, you move your cursor and so on, and the system is telling you what you see is what you get, meaning what you see now on the screen, don't care how I memorize this instruction, but is what you will get when you print this document or when you will visualize this document again on a screen. So this is was the new generation of editors that came out in the late 80s, and this is what we are used today. And there is a number of these editors. And if we keep going on, therefore, where is the cursor here? The Postscript, as I said before, let's not get into too many details. I will put the slides on the website, so if you can look at them, and if you have questions tomorrow, or you send me an email, we can talk offline. So Postscript is really a way in which you describe rather the way in which the content will be rendered on a piece of paper or on a screen. So it is really, let me say, a set of instructions. It's like a program, as it says. It's like a program that has in mind how a printing head should be moved in order to render the document that it's represented in Postscript. And as we say here, so the actual text inside the document is not always immediate, because the description of Postscript is not based on the text, on the character, but is based on how you print them. So how you move the printing head up, down, left, right, and so on. So this is the basic idea. The next one is PDF is the evolution of Postscript. This is now proprietary from Adobe. But PDF started again as a Postscript type of representation. Today has evolved, let me say, in a more complete representation, in which you have some kind of interaction with the document. You have limited editing capabilities, meaning that you are able to replace some pieces of text. You can search in the documents. You can access the pages in a random way rather than in sequential way, meaning that you would have to go through all the previous pages to reach the N1 and so on. So PDF is one of the most common, I would say, is the most common format for exchanging data, in which you do not really need to interact with the data, meaning to edit, to change too much. So it's considered the final form of a document that you exchange. And actually, there is also a set of conventions, which is called PDF-A, in which if you write your PDF document following these recommendations, it is considered as a standard for archiving, meaning that it is expected that this format should be always available, even in the next decades, as long as you use the PDF functions in the way it is suggested in this PDF-A. And I put archiving in quotes because archiving here is meant not really to be put in an archive, but archiving means to be stored somewhere forever, meaning that you hope to be able to retrieve this PDF document maybe 20 years from now, which is, we will get back to this point, which is not a given. It's not so clear. This is one of the main difference between a library and the digital libraries, meaning that in a library you put a book on a shelf and more or less you would expect that 50 years later somebody else will go back and take the same book and everything will be okay. If you put something on a disk, even a PDF file, and you do not know if 50 years from now somebody will really be able to read that document. So we will get back a little bit to this one. Now we have a number of let me say, of text editors, different formats. All of them, I mean, except the last one, which is Word, are more or less, let me say, making it clear the difference between the text and the instructions on how to format this text. So one of the first one was this RTF, rich text format. Another one is ODF, which is becoming more and more common as an open source replacement for Word. So this is internally, this is basically an XML document. We will come back also to what is an XML document, but compressed, so that is a very compact format. And you have all the possibility to represent a document, text, spreadsheet like Excel, presentation like PowerPoint, graphic, and so on. And as I was saying, it is more and more becoming used as a free software replacement for Word, which is a proprietary program. The next one, this may be of less interest in the humanities because LaTeX, this is the key, the Greek letters key, so it's pronounced LaTeX. And this is very much used in mathematics and chemistry because with this with this type of document format, it is very easy, but between quotes. It is possible without too many complications to represent mathematical formulas or chemical compounds and so on. And so this is in computer science and especially the humanities is not much used. In chemistry, mathematics is is the most common language. There are some journals that when you submit a paper to the journal, they accept the paper only if you submit in LaTeX format, not in PDF. So it is very, very popular. And then there is the most used one. I mean, most used just because Windows is the most used, and I mean, Word comes for free with Windows, which, however, has the problem of being a proprietary format. And after, let me say, the 90s, I think that Microsoft has no longer published the internal format of a Word file. So it is very difficult to interact with a file, with a doc or docx file, unless you use actually Word. And in many applications in which you need to extract text from a file. So the idea is this is especially for information retrieval applications, you need to extract the pure text from the document regardless of the format. And therefore you need the programs that go through the document and just extract the text and forget about formatting. Now, for all the other formats that we have seen, that is relatively easy. Postscript is not that easy, but it can be done. Word is really difficult. So the suggestion here again, if you're dealing in projects in which then you know that your document, there will be some applications that will need to extract text from your document, you may want to consider to save your Word document in a different format like ODT, RTF, HTML, that are all formats supported by Word. So when again, also TXT actually. TXT is really if you expect that the next user of your text will be a program. If it is for human, I would rather suggest ODT or RTF. So this is a very brief overview of the different, how you can, let me say, package the text contents within the computer, because the text is just the raw material, but actually all these files, as I was saying, contain some kind of formatting instructions. This is the idea. Images. Now we enter into a little bit, this is for maybe the most complicated part of how you represent things, images, video, and audio, because it's not so immediate how you represent an image with numbers. So now, how you represent an image with numbers. I like to go through this one just to relax, because image processing, where image compression, representation and compression is a big chapter, was a very popular topic of research in the 80s. Why the 80s? Because at that point, at that time, I mean, the computing power of computers and the memories became big enough that you could really start thinking of real applications dealing with images. Before that, it was difficult because the computers were not fast enough, and especially memories were not big enough to deal with images, because as we will see in a moment, images require much more memory, or if you want, files containing images are usually much more bigger than files containing just text. And those two images, very, very popular, they were text beds. For example, this one was very popular because it has two characteristics, very large areas of the same color and very large areas with very fine textures. Or you think of this, all the hair here, which are very good for testing programs that have to do with image processing and so on. And this picture here has a lot of middle tones. I mean, let me say, based on the same color, but a number of different levels of the colors. So those were the two main test beds for image processing. But this is just because I like those two pictures. We were saying representation. Now, there are two big families. We will talk about one. The one that is called vector formats, which means that you represent your image with its geometric components. So you describe the image with lines and curves and circles and solids and so on, each one with a color, with the textures and so on. But basically your picture is reconstructed with a number of geometrical figures, geometrical components that are described in a geometrical way. And the most common format that you see is SVG, Scalable Vector Graphics. That is the format, for example, that is recommended for pictures that you put on Wikipedia. It is recommended that pictures you put there, they are in SVG. And it become very, very, very common with this other format, SWF, which was the Flash player also for small movies, animated images. Now it has been replaced by Shockwave, I think, by Adobe, and the Flash player, as it was known, is no longer supported. So those are, let me say, And the main advantage of representing images with vector graphics is that they are scalable. Meaning that you can represent, actually render the image on a paper or on a screen, whatever the size, without losing any detail, because they're just being mathematical functions. Once that you know that it is a circle, you can draw the circle at the size you want if you want to show on a screen, so you can scale up and down the image without any loss of information. While we will see that with the raster formats, when you scale up and down, especially if you scale too much down, you lose information. And if you scale up at some point, you will start detecting that is no longer a real picture, but is a raster picture. And what is raster? What is raster is that you represent the image. So you have an image. What you do, you divide the image in small squares or picture elements, and that's the name is pixel, is just the construction of picture elements. And you make each pixel small enough so that you can represent it in the computer with one, let me say one, or with one number that represents its color. So the basic idea is that each pixel has a uniform color. And at this point, what you are doing to represent in the computer the picture is to represent the sequence of numbers that represent the colors of each pixel along the row and the next row and so on. So you see that now you can, now that we have understood the trick, let me say, it's easy to represent every type of pictures within the computer. Of course, there are, things to consider. First of all, the first question that you should pose yourself is, okay, but how many pixels do I want or do I need to put in a picture? Now, that really depends on the applications. And let me say that in real life, there are basically three ways in which you can measure, you can understand the quality of a picture. One is that is the most popular one, is the digital cameras. Now it's now more than 20 years that you no longer have camera with the film, with the pellicola. And now, for example, therefore, what you ask when you buy a new camera, the first thing that you look at is how many megapixels it has, which means how many pixels will be used by the camera to take the picture. And they started with 5 megapixels. And today, let me say, camera of today, they are in the range of 10, 15 megapixel, which means that a picture taken with this camera or with your phone, the smartphone. The last generation, I think the Samsung, I don't remember the Apple, but the Samsung has one camera with 45 megapixel, which means that one picture has 45 millions of dots of pixels to represent the picture. So it's a good representation. So the other way in which you can measure the accuracy of representing a picture is on TV. The TV also now, the TV of today are all digital. And there what you count is the number of rows and the number of columns. And as you all know, the high definition TV that has become the standard in the last few years has about 2,000 columns and about 1,000 lines. Now the market is pushing very much for the so-called 4K, which is doubling, let me say, the resolution and doubling also not doubling the size of the screen, but increasing. And that means that if 4K, you have almost 4,000 columns and more than 2,000 rows. So this is the resolution of real things. On a PC screen, again, when you buy a new PC, a portable, the standard one is this one. If you want to pay a little bit more, you can move to those two standards of screens. But we are in this range. For portable computers, it's not that much. And finally, the last way in which you measure the number of pixels is with this measure called the DPI, dots per inch, which means how many pixels are in an inch of image. And those are mostly used for the scanners or for printing machines. And here again, the range is, I mean, today you can buy very cheaply for 50 euros a scanner with 2400 dots per inch, meaning that every 2.5 centimeter of the scanned image, you will have 2400 pixels. So that gives you a good, again, resolution. So those are the running, let me say, normal data. The other question that you should pose is, okay, now I know how many pixels I have in a picture, but how many bits do I need in order to represent a pixel? Because we have seen before that the more bits you have, the bigger number you can use. And therefore, really, the question is, how many level of the color do I want to represent? We have said that one pixel is just one color. I mean, the pixel has to be small enough to be considered a uniform of just one color. So is how many bits do I want to spend to represent this color, which in other words means how many shades or how many tonalities of this color will have. And clearly, for example, for black and white, which is typical of the fax machines, you need 1 bit because you only need to say whether it is black or it is white. And so with 1 bit, you are done. So the fax machines are the most compact. For color images, which is most of the applications on the web, you need more bits because usually colors are represented with 3 numbers, not with just one. And why with 3 numbers? Because the physiology of the eye, I move to the next one then I will come back. The physiology of the eye was something that was found, let me say, in the 30s, but found real applications in the 40s and the 50s with the first TV color. However, the human eye is the detecting colors because the eye is a vibration, a radiation that is hitting the eye with different frequencies. And it is shown that the eye can see, let me say, the light and the colors in a very precise and narrow range of frequencies. And let me say, the radiation that hits your eye below the smallest frequency, you do not see as light, but you perceive as heat. These are the infrared. You have a number of infrared stoves or things because they are emitting, let me say, light that is not seen by the eye, but is perceived by your skin as heat. And on the other end of the spectrum of the frequency, you have the ultraviolet, which means again that this is light that you do not see with the eye, but you feel with your skin because you get sunburned when you stay too much at the sun, or if you stay with reasonably, you get tanned without being burned. But that is the effect of the ultraviolet rays that are part of the light emitted by the sun. And so our eye is only able to see, let me say, this small portion of, let me call it, this radiation. Now, the study has shown that I can recreate, let me say, the same stimulation of the eye. I can generate, let me say, any color that my eye can see, just mixing in the proper way 3 basic colors, the red, the green, and the blue. So if I have 3, let me say, lamps emitting, one emitting only red light, one only green light, one only blue light, if I mix them with the appropriate intensity, I can generate all the possible colors that my eye is able to see. So based on this idea, and I try to get back one slide if I can. Let me see if I can. Yes. So that means, therefore, that in order to represent the color of a pixel, the idea is to represent this color with 3 numbers, where each number represents the intensity of the red, the intensity of the green, and the intensity of the blue. And now we are finally to the point where, okay, now how many bits do I want to spend for one color? The standard today is to use basically 16 bits for each color, and therefore 1 pixel is represented with 16 plus 16 plus 16, which makes 48 bits to represent one color, which represents a lot of colors, because I mean, mixing them in any way, you represent even more than our human eye is able to detect. However, the conclusion of all of this is that, therefore, you can start understanding that if I have a picture with 50 megapixel, I have a good camera, so I have 50 megapixel. And if each pixel is taking 50 bits, okay, we go up very fast in the number of bytes that I need in order to handle and to store this picture. So this is the beginning. And now, if we go on, this is the same idea for printing. I mean, in this case, the RGB is for the light that is being emitted by a lamp. For the printers, the light is not emitted, but is reflected by the piece of paper. But the mechanism is the same, and therefore you have another 3 basic colors that are the cyan, magenta, and yellow, that are the 3 colors that you use in your printers. In order to get mixing them, you get all the colors. But the idea is basically the same, to mix those colors in order that your eye is able to detect the proper color. And now you have a number of formats for images. And here, let me say this way, now I'm having a number of slides, but I will not deal with too much with them. You can have a look and send me a question or raise your hand later for further explanations. But however, the point is that now, from what I've stated until now, it should be clear that in the field of image representation, there is the need to compress the images, because otherwise, if we take the image as they come out from a scanner or from a digital camera, they would be too big in order to be handled, or I mean, the program could handle them, but you would need too much RAM, too much storage. So the idea is that for all practical applications, what you want to do, you want to take the image as it comes out of the sensor. And then at this point, you want to compress, meaning using less bits in order that the handling and the managing of these pictures becomes easier. And you have 2 big families of compression algorithms. One family is the compression without loss, meaning that you and again, I move to the next slide and then I come back here. What means compression? Compression means that you have some information represented here as a sequence of bits. You take this information through an algorithm, an encoder, that takes this information and transforms this into a smaller number of bits. So the compression really mean to do some mathematical operation or some, let me say, processing of this information in order that the result of the coding has less bits than has the original information. And why you do that? I mean, this is not has been invented now with the images. Now this dates back 30, 40 years, because you want to do, I mean, the reason for decreasing the size of the information is that if you store that on a disk, you're going to use less disk space. And especially 30, 40 years ago, disk space was very, very expensive. So it was worth taking the time to compress the image if you could save some space on disk. Or, which is equally important, if you want to send this information over a network, because you are downloading an image from some web server, and therefore the image has to go over the network and to arrive to your PC, Okay, you want to decrease the size of the image that you are sending over the network because you don't want to, let me say to you, you want to use the network for as little as possible, not to clog the network. I mean, if everybody would send millions of bytes over the network at some point, it's like the roads. I mean, if you have too many cars, you have a traffic jam. So if you send too many bits on a network, you have a network jam. And today, I mean, the technology is such that we can handle that. But again, especially 20, 30 years ago, was not that the case. So compression was a very important branch of research. And however, I finish my story. Once that the information has arrived to destination, if it is on the net, sent on the network, or once that you need to take out from storage, from the external memory, the information and you want to bring it back into the memory, you have to decompress the information with a decoder. And here is the difference. Now that the algorithm of the lossless compression means that here you are able, by magic, we can see in a moment, that if you enter with 1000 bits, you come out with 500 bits. But however, when you arrive here and you put in the decoder your 500 bits, what you get out are the original 1000 bits, and not only 1000, but really exactly the same one bit by bit. So the information here, uncompressed, is exactly the same as the information that you put here. So this is the lossless. Now, and clearly there is an extent to which you can compress, because at some point, because conceptually speaking, compression trying to operate on how you represent the information, but there is practical limits to the way in which you can represent the information. Below which you cannot go, otherwise you would lose information. And this is what happens with the lossy compression, meaning that with the lossy compression, you can compress much more. But why you can compress much more? Because you throw away information. And we will see in a moment, especially for images, which information do you throw away? Again, the physiology of the eye, I mean, the doctors have seen and understood that there are, let me say, that our eye is not a perfect, let me say, detecting device for colors and images, but our eye is not able to perceive very frequent, but whenever I say very frequent, I mean really thousands of times, variations in colors or variations in texture. So our eye is really making an average, let me say, of the scene that it's seeing. So that means, therefore, that if I can find some algorithm by which I can throw away the parts that my eye is not able to see, when I decompress the image and will render the image on a screen, I will not see the difference, because there are things that my eye was not detecting before compression. I throw them away and I look at the new image, and my eye will see no difference, because I was not seeing them before, and I cannot detect now that they are no longer there. So this is the basic idea behind the lossy compression. And so going back here, therefore, the main format for lossless compressions are these are called G3 and G4 that are used in fax, because fax, clearly you don't want to have to fax a page and then what you get at the arrival is something different. So you want to make sure that in fax there is a lossless compression. And there is also a very popular format that is GIF or GIF, depending on how you pronounce it, which is very common for very small images and very common now on the web, especially with smartphones. The animated GIF, you have the butterfly moving the wings and some character jumping up and down and so on. So it is very easy to represent them with GIF. The bulk of the image processing is based instead of images coming from camera, from movies and other things. And here you have instead a format called JPEG, that is, say it is very much compressing, but this is the one that is trying to throw away the part of the picture that our eye cannot see. And as long as I'm here, that I can anticipate, now we will see them in a moment. Let me try now to few words of explanation. Now, I'm going to skip the basic ideas behind the compression. Because you may ask, but how can I do the magic of compressing without losing information? The main algorithm here is that there are two of them. One is the Huffman coding, and the other one is the zip, or the RAR that you have seen. And the two of them are based on two different ideas. The idea of Huffman is based on coding the symbol, the most frequent symbol with less bits than the more frequent symbols, which means that you are coding, let me state it this way, with the character representation that you have seen before. For example, the ASCII 8 bits, let's say the ASCII, which is more simple. Each character occupies 8 bits. But now the idea of, and so therefore, when you send a string of characters, each one will, let me say, will account for 8 bits for 1 byte. Now, the idea of Huffman that was taken, this is why I like the history, was invented, was understood by Morse in 1850. Was that you can represent the more frequent symbols of an alphabet with fewer characters than the less frequent symbols. So Morse, for example, decided, you know what is the Morse alphabet. We have seen, I hope you have seen in the movies. It's a representation of the alphabet with the electric signal, and they are represented with the dots and dash. And so that will usually correspond to a short sound or to a long sound. And that was the, let me say, the telegraph alphabet. And Morse just understood that for the convenience of who was transmitting and receiving, it was good to have short codes for the very frequent letters and longer codes for the long ones. So the E, that is the most frequent letter in English, is just 1 dot. And the T, that is the next one, is just a 1 dash. And then you go on. Now, Huffman was more or less doing the same. Just saying where it is here. Let me go on. Yes. No, I don't have this one. In any case, the idea of Huffman is to represent the most common characters with few bits, and the less common characters with more bits. And you can get compression ratio very good depending on the alphabet. The other idea that you have here is instead the dictionary coding is based on this one. This one. In which, so this is the string of characters that you want to compress. This is the idea. And therefore, let me say, the coder is just outputting the code. Now, the idea is that when you find in this string a substring that you have already seen in the past, because I say in the past because if I go back of a few, shall I be able? Yes. If I go back to this picture, you see that the way that the encoder works is that you feed the information here, 1 character or 1 symbol at a time, and what you get here is the output of the encoder. And the same that happens for the decoding. You input here 1 symbol at a time of the compressed information, and you get here the symbol of the uncompressed information. And so the idea here is that if the encoder at some point finds a substring that has already seen in the past, so in this example 2b, which is a sequence of 5 characters, T, O, blank, BE. Now, the encoder recognizes that this string has already happened in the past. Therefore, instead of using these 5 characters, in the coded information, it will put the information that says, okay, go back to position number 1 and take the string of a length of 5. So in this position, after not, you don't have in the compressed string the 5 characters of 2B, but you have instead you have 2 numbers, and the decoder will be smart enough to understand those 2 numbers, go back to position 1, take the string of length 5, and insert these strings into the decoded string. So this is the basic idea or underlying the dictionary coding, and it's called the Lempel-Ziv because those are the 2 authors that published this algorithm in 77. As I was saying before, the 70s and the 80s were the years in which compression was one of the hot topic for research. If we keep going, now I will skip this one. This is just to explain again this notion of the dictionary encoding. From this string, you encode this one here. You say that after an A, you go back to position 1 and you take a string of length 16th, which is this string here that goes from here to here. Then you have an R, then you go back to position 18 and so on. But this is, you can look at that. And the idea of this dictionary encoding is how you actually build. Okay, the idea is that in reality, what you do, the encoder today, the zip and the rar, you start with the dictionary that is already filled with all the characters, so with the 127 ASCII characters. And as the system, the encoder is compressing the input string, it will build all the substrings in this dictionary. So it says every time that it finds a new character, we'll insert this one with the next character in the dictionary. So the encoder will see an A. It knows that then next will come a B, and therefore it say, okay, now I have seen a substring AB, and I put this a new entry in the dictionary. Then it goes on and it says another strings BA, and it puts these strings in the dictionary. Then it goes on AA, and it puts it in the dictionary. And then finally it finds another one, which is ABA, which is this one, and it puts this one again. So what it's saying is that the output of the compressed string is no longer the string of characters here, but is the sequence of entries in the dictionary. So what is the output of the encoder is this sequence of number. And the decoder will work exactly the same way, starting with the initial vocabulary that is known by both of them, I mean the encoder and the decoder, and we'll be able to build the same dictionary and therefore to translate this sequence of number into a sequence of character. This is the basic idea. And this is the foundation, as I was saying before, of a family of compressor that was very popular, you see, between the 70s and the 2000s. Those are the different algorithms. Huffman, the good Huffman came out in 56, was a doctoral thesis. Computers were not yet, I mean, it was not so hot, but was a bet between Huffman and his supervisor about this one. But then nothing happened until the 70s, when compression became very interesting and popular. And you see how many algorithms have been there, not all of the here. But somehow, after 2000, there is no longer interest because we have, I mean, the compressor have reached more or less the theoretical limit, which is 2.5 something, if you want to compress an 8-bit character, below which you start losing information. So you can mathematically prove that you will not be able to go below this compression rate. If you keep, at some point you will start losing information. So this is the overview of the compression. And now, this we will skip them. I mean the internal format. Just let's remember that G3 is specific for fax. G3 and G4 is specific for compressing fax images. And the idea and the basis of the fax images is that this is one line of a fax as taken from a scanner. So it is typically for a typewritten piece of paper. So the black is just the leg of the letters. Like this, you see this R as a small black, and there is a white here. So the idea is that you compress with Huffman this sequence of zero of black and white. This is the table of compression, and therefore what you replace is from a sequence of bits that they should be really 1 0 1 0 this way. Instead, you replace a run length, let me say a sequence of bits of the same color with those code here, and you get a very, very good compression. This is the basic idea behind G3 and G4. GIF is called, what I say is, and let me go directly here, is called the lossless compression, which is really not true. With GIF, you want to represent color images. And therefore, the idea behind GIF is what? That you define a palette of 256 colors. So you have to, which are the most representative 256 color of the image that you are going to compress. And then in the compressed image, instead of putting the real color of the pixel, which can be up to 48 bits, in the compressed image, what you do, you put the index in this table of the color. So that means that instead of having a pixel that is taking 48 bits, in this table, you have the same pixel that is represented by 8 bits, because this is what you need in order to address a 256 table. You just need 8 bits. So you do all of that. At the end of this one, what you do, you compress this table here of pointers with Huffman. If we go back, we can see this one. If we go back, you have with Huffman. And at this point, you finally compress everything with the zip, the Lempel zip algorithm. So this is the idea in which you can compress really this format. This is, I was saying, however, it's called lossless because once that you start with this table here, you do not have any further loss of information. However, there is an original loss of information because you are actually coding only 256 color instead of the original ones that maybe were much more. So this is the basic idea. The JPEG is what is the most common, and JPEG is doing what? JPEG, as I was saying before, is really taking advantage of the fact that our eye is really not able to detect very frequent variations in the image. And therefore, there is a very complex algorithm because it is why it is very complex. Because the first step that you have to do, and let's see if you can see here, the first step, first of all, you cannot compress the image, the whole image as a whole. But what you do is, first of all, you compress each color channel by itself. So you compress the red, the green, and the blue separately. And then each image in one color, you divide in small blocks. So these are blocks of 8 by 8 pixels, and you compress separately each block. And the key point, I mean, the idea of the whole algorithm is that if you look at the pixel, you cannot detect the variation. I mean, even if you look at the real picture, your eye is not seeing the variation. So what you have to do is to apply a mathematical transform that is transforming, let me say, the variation of colors in the space into the frequency of variation into a frequency domain. And so this is called is the two-dimensional equivalent of the Fourier transform, if somebody may remember doing some studies at the high school, the Fourier transform. And therefore, what you do is, first of all, you make a mathematical transformation to this 8 by 8 original image. And you get another matrix of 8 by 8. Here is the step in which you throw away the information. The result that you obtain is again compressed with Huffman. And this is the final result of your small block. And you do that for all the pictures. let me say, the decoding is clearly the same, meaning, it's the inverse, meaning that you decode the half-band coding, you dequantize, but the point is that the information that was thrown away here, you cannot recover here because it does not exist any longer. So therefore, when you dequantize, you only get the information that was maintained in this step here. Then you do the inverse transform, meaning you go back from the frequency domain to the space domain, and you finally have the pixel. Now, to follow this one in the real, but again, just for out of curiosity, so to speak, you start with those are the value of the pixels. So those are numbers that usually goes between 0 and 256. So this, let's say that this is the red channel, and those are the intensity of the red color in this point of the image and so on. Now, what you do is, if this mathematical transform, you transform this one in the coefficients of the frequencies. And you know, given these mathematical functions, that on this corner here, you have the low frequencies. And in this corner here, you have the high frequencies. So what you want to do is you want to get rid, let me say, of all this part of the frequencies, because you know, or you assume that your eyes will not be able, have not seen them and will not detect if they disappear. So in the next step, what you do is that you use this, let me say, quantization matrix in order, with a simple multiplication and division, in order to get rid, let me say, of those things. And the result that you obtain is this one, where the zeros represent all the information that you have thrown away. And you see, you try to keep as much as you can in this upper left corner, because you know that is the section where the low frequencies are. So you want to keep them, and you can throw away all of them. Then what you do is you zigzag, you linearize the matrix in this way. And why in this way? Because you want to take advantage of the long sequences of 0, because then you compress with Huffman this linearized matrix. And finally, you arrive to the point. Now, when you go back after you decode from Huffman, this is what I was saying before. Since this is the matrix that you receive, when you dequantize, meaning you try to get back the original coefficient, where there was 0, it remains 0. This is the information that was lost, that was thrown away. However, and this is the trick, the magic, when you go through, let me say, the inverse cosine transform, meaning you go from the frequency to the space domain again, now you get the real values of the pixel. And if you compare them with the original, you see that there is, yes, some difference, but not that much. So here you have 154, here you have 149, 134, 123. So you have to think that these maybe are, again, pixel of out of 10 billion pixels in the whole picture. So this small variation is really small. And this is the way that your final image, you can, let me say, reconstruct and show on a screen or print on a paper. And unless you are really an expert, you will not be able to detect that the image has been compressed and decompressed any longer. So this is those last two are just for curiosity, because they are not much used in computer, but some, let me say, professional photographers, they were complaining that with digital cameras was no longer able to do tricks that you used to do in developing, let me say, the film and in printing on paper, in which you could have special effects, black and white, or other things. So what I'm saying is that an image that has gone through JPEG is no longer the original image. You have lost some information. And some of professional photographers are claiming that they might want to have also that information, because with chemical things or other things, they were able to do other things to maintain some of that information. So most of the high range digital camera that you can buy today, they also provided what is called the sensor output, which is a format called RAW or DNG, digital negative, meaning that the camera now today, most of the digital camera, when you download the pictures on your PC or somewhere else, you download directly the JPEG image, meaning that you download the compressed image. You download the image without the lost information. If you want, you can have options in which you can download the sensor output, meaning the original value says they were taken by the sensor, so your 50 megapixel, each one with its original value, and then you can process them with Photoshop or other things, and you can obtain, let me say, other special photographic effects. So this is the idea. And the last thing that may be interesting to know is TIFF, let me say which is not a format of an image, but TIFF is an image container, which is basically the possibility of having in the same file an image, which can be black and white, grayscale, full color. Palette color is the GIF, full color is the JPEG. Together with a number of additional information, or just to use the right term, together with a number of metadata describing this picture. And TIFF is becoming, again, I mean, a special version of TIFF is becoming more or less the standard for archiving images, the same as PDFA. TIFF is one of the most used for exchanging images between archives or between organizations. This is one of the most popular, so that's why I'm using. I will try to go as quickly as possible, which is video. Video at this point should be, now that we start, what is a video? Video is definitely, as we all know, video was invented, the movie were invented by Lumiere at the end of 1800. And it's also, again, just using a characteristic of our eye, meaning that if we present to our eye a sequence of images very quickly, let's say like 25 or 30 images per second, our eye will not be able to detect that they are, let me say, 30 different images, but our eye will interpolate between them, and what we will see is the effect of movement. So this is the idea that the Lumiere brothers had in 1895, and that was the birth of the movie industry. So in any case, that means that a movie is really a sequence of images. I mean, 30 images per second, but if you look into a movie, you are actually just looking at a sequence of photographs, so to speak. And here you can understand again that therefore, in order to digitize a movie, you still need a lot of bits. And because now we are going, what I was mentioning before, into the TV standards. So how many rows and how many columns are in a TV screen. And the initial standards were NTSC and PAL. NTSC was mostly used in the US, PAL was mostly used in Europe, and they were standard. For example, the NTSC PAL were having 576 rows and 768 columns on a screen. We have seen before that now we have quickly moved to HD high definition TV with these numbers, and to this 4K. Then you have this intermediate step with ultra high definition, and the last one that the market is pushing, I mean, trying to encourage people to buy new TV sets with the 4K, which has about 2,000 rows and 4,000 columns. So if you think, therefore, at this point, each image has this size, and you have 30 of these images in each second of movie, you can quickly imagine how many bits you need in order to represent a movie. So therefore, the idea of compression I mean, this is just a small computation with the normal resolution. I mean, high definition TV and 30 frames per second and 24 images. 34. I don't remember the 34. 30 images. Okay, 24-bit is just the number, the number of bits that you need to represent one image in this compression. In any case, you need it in the order of 1 gigabyte per second. So this is really the way that we want to compress. And the compression here again, you have two types of compression in a movie. One is that you take a specific frame. So when I say frame, I mean one picture in one of those. You take a specific frame and you compress in the JPEG way. So you see, this is again what we have seen before. Here you make a different representation of colors, but then you start with your image in one color. You divide in block. You make the discrete cosine transform, you go into the frequency, you throw away all the things that your eyes is not supposed to see, you compress with Huffman, and you get a compressed image. Now, this is done not on all the images, because this compression would not be enough for the movie. So therefore, there is another type of compression that is done for the movie, which takes, let me say, advantage of this fact that since the frames, the images are very close one to the other in time, the difference between one frame and the previous one is usually very small. So this is, for example, is a graph showing the number of pixels that have changed over time when there is a speaker talking on TV. And you see that less than 10% of the pixel remains the same, and you have small changes only when in 2 seconds when there is a movement of the head or things like that. So in any case, the basic idea is therefore that what you do in order to encode a frame is to encode really the difference between a frame and the previous one. And the difference meaning that you try to keep track of what has changed from one frame to the next one. So here, for example, you can see that this player has moved a little bit from this position to this position. Therefore, in the compressed frame here, you are not going to put all the information about this head, but you only put the information about the movement of this head from this position to this position. And for example, all the green remain the same, so you do not need to put any information in this frame here. So this is the way in which you compress frame, taking advantage of what is called the temporal redundancy, meaning that since you know that the frames comes one after the other at 1/30th of a second of interval, you take advantage of the fact that the changes are very small. And therefore, in the reality, let me say, compression algorithms of today, you compress the frames in 3 different ways. The high frames that are the ones, the reference ones, that we have seen are the ones that you compress regardless of the previous and the following ones. So then you are able to decompress them without knowing anything about the previous frames or the next frames. Then you have a second category of frames that you compress instead, are called predictive coded, that you compress taking into consideration all the frames that you have seen before, therefore the previous frame. And then finally, that are the most frequent ones, you encode also the B frames, which are the ones in which that you can, let me say, code, taking advantage of your knowledge of the previous ones and the next ones, meaning that somehow, and this is how you can do, because you can think that the encoder, meaning has the same altogether. I mean, it's not really that the decoder will see the frames one after the other, but the encoder has the frames altogether. So the encoder can take what? This one is the reference frames coded with this I, meaning the reference frame that does not need anything. Then it can encode the pre-frames that can have the knowledge only of the previous one. Therefore, the pre-frame and the pre-frame here, they need to know only the previous ones. But then having all of them together, the encoder can encode those B frames, taking knowledge of the past ones and the next ones. And that means that therefore the difference or the way that can be encoded is really very compact, because to go into the real detail means that the coding, the way that you encode those B frames is that not real, you do not really encode the difference, but what you do is that you build a model of how the frames are changing. And what you do here in this algorithm, you make a model of what will be the next frame, and then what you encode is the difference between the real next frames and the frame that you have just encoded. And if your algorithm of prediction, that's why it is called predictive frames, you see. And if your prediction algorithm is very good, that means that the difference between your prediction and the actual real frame is so small that you will be able to codify this difference in very few bits. And this is the number we are getting, so that with the free frames we have a compression rate of 1 to 50, again without losing any, I mean without losing information, but without losing any quality, meaning that in the end our eye will not be able to detect this type of compression. So this is what we normally see on our TV when you do the streaming, or what you're actually seeing on your screen now on these Teams things is really video that has been coded in this way. The audio, the last step, then you will survive for this morning. the audio is what? The audio, you may imagine, how can you change the audio in numbers? Well, what is the audio? The audio is a signal which is that is actually in real life is a compression wave in the air that is hitting your ear, and you hear the sound. Your brain will translate this, let me say, this hitting of the air on your ear into sound. Now, so your problem is how can you represent a wave, a signal that changes over time in a sequence of number? Well, you can sample, let me say, meaning that you measure the signal at time interval, fixed time intervals, so that it's called you sample the interval, and you register the height, the intensity of this curve at each time that you measure it. And you register, so to speak, the amplitude of this signal. So that means that in the end, at the end of your sampling, what you will have, you have no longer the signal, but you have a sequence of numbers, each one representing the height of the signal at each instant in time. And so therefore, that means that if you want to reconstruct this signal when you have no longer the things, what you will get instead of the gray line here, what you will get is the red line here. But now you can imagine that if the frequency is small enough so that you take the sample at very small interval along the signal, then the red line will be quite similar. I mean, actually will be almost the same as the original signal. So this is the basic idea to represent the signal as a sequence of number, just to represent the value of the signals over a number of small intervals of time. And to give you some numbers, to take you the mathematics, again, what we are going to do is we are going to compress the sound in the same way as the picture, because again here we take advantage of the physiology of the ear, meaning the sound, as I was saying before, is a compression, a wave in the air that is hitting your ear. And this wave is done of many frequencies. I mean, it has a frequency, but it is composed, that is the Fourier theorem. You can think that this signal that we are seeing here is really obtained as the sum of a number of sinusoidal signal with increasing frequencies. And therefore, we know again, we know the doctors have detected that our ear can detect vibrations that arrive to the ear that goes from 15 to 20 kilohertz, meaning vibrations per second, to about 20,000 kilohertz, to 20,000 hertz. Beyond that, you have the ultrasound, meaning that you still have this vibration, but your ear is not able to hear that. Actually, if the power of this vibration is too much, you have a pain in the ear, because I mean, it is still hitting your ear. But for example, ultrasound is used for the training of dogs, because the ear of dogs is able to hear instead much higher frequencies, and so you have special whistles with which you can train dogs, just blowing in this whistle, and the dog will obey because it will hear the signal. The human will not hear it. However, this was a digression. However, the next question is the question that you have is, okay, how many samples per second should I have in order not to lose too much information when I sample my sound? Well, here we have another theorem from Shannon that says that you have to sample at a rate which should be at least the double of the highest frequency that you want to maintain in your sample. So going back to real numbers, if we want to keep up to the frequency up to 20 kilohertz, which are the ones that our ear is able to perceive, we will have to sample with a rate that has to be more than 40 kilohertz, and the standard numbers are 44 or 48. So in any case, the end of all this thing is that in order to transform a sound in numbers, you have to measure, so to speak, the sound 44,000 times per second, and you record, or you write down the number, the intensity of the sound in each of the sample. And so you have transformed 1 second of sound into a sequence of 40,000 numbers. This is the idea. Then what you do with these numbers? Well, okay, now we know the trick. This is a different picture, but we go again through the same process as the pictures, meaning that we transform this sound into the frequency domain. We throw away all the frequencies that are not needed. There is even an acoustic model of the ear that will help in throwing away even more frequencies, because there are some phenomena. But in the end, what we do, we just take the resulting matrix, we encode with Huffman, and we get a bit stream in output. So again, we can forget about all of this, that we all know that it is MP3. We all are using with cell phones and the rest, all the music that we're hearing out of our phones or TV now is mostly MP3. Just for your curiosity, MP3 comes from the standard. MPEG is the movie picture expert group that is the one that over the years has defined all these algorithms of compression. And just at the beginning, so MPEG-1 was the first one, they defined 3 different ways of compressed sound. MPEG-3 is the 3rd layer, and this is what has remained because it's the most effective, the most common. And just again to give real word, that without any compression and with the sampling of about 16 bits per sample, the sound would be the equivalent of 768 kilobits per second. So we would need to transfer or to handle this number of bits per second. Now, after compression, depending on this loop here, how much information you can throw away, you can transform your sound in a stream that goes, let me say, from 32 kilobits per second up to not just 192, but 256 kilobits per second, depending again on how much information you want to throw away. And I do not know if you have ripped some audio CD with Windows, in which means RIP, that means that you take the audio CD where the signal is analog and you transform the song or the music into an MP3 file. And again, if you open the Windows Media Player, if you open this, let me say, RIP function, in which you take the CD and you store the music in MP3, you can open the Windows with the options, the parameters, and you can see that you can set, let me say, the quality of the digital audio up to, I think, from 64 up to 256 kilobits per second. But to give you an idea, for normal music, I mean jazz or disco music, 128 kilobits per second is more than enough. You normally would not be able to tell the difference between the original analog audio and the digital audio, the MP3 song that you have. If you go to classical music, that it is a little bit more sophisticated, you should go up to 192. The next step is about 192 kilobits per second. And that, again, for most of the people is unable to distinguish between the original sound and the MP3 sound. I would say that just orchestra directors and things like that would be able to tell the difference between the original sound and the MP3 sound. But if you go up to 256, I think there have been experiments, not even music directors have been able to tell the difference that was an MP3 music at 256 kilobytes. So I would say for all our practical applications, MP3 at 128 or 192 is more than enough. This is the last one, which says, okay, how do we deal, however? We do not see very much this type of files. What we see are those files, which are the files of the complete movie. However, this format of files that we see around, I mean, OGG, MP4, now we see very much, for example, YouTube. Most of the files that you upload to YouTube are MP4, but all these formats of files are not really format of the images or the sound, but they are containers. They are called Muxer, which is the abbreviation of multiplexer, because those are files that contain the audio, the video stream and the audio stream. And each they can contain more than one. For example, for stereo, they can contain one video stream and two audio stream. One is the right channel, one is the left channel. And what is again, what is interesting is that you should know, or in some applications, it would be good to know what are the codecs that are actually being used in order to compress both the audio and the video. And here are the names of the most common codecs that are around. And for example, for the digital TV, that in Italy now we are moving to a new standard of digital TV. I've seen some advertising that you should change your tuner and things like that, because now we're moving, the digital TV is moving to H256 as the compression of the video. I do not know which one is the compression of the audio. However, the most common compression for the audio are those three that I've seen: ASC, AC3, and MP3. MP3 is ubiquitous, meaning you can find everywhere. So this gives you how, that, again, as seen from the inside, all the kind of information that you can find and you encounter in your applications. Video can be interesting because more and more, for example, you start having applications that have to do with videos. I mean, even if they are in the humanities, for example, when you collect, Enrica, you know better, you collect interviews with people, the disappearing habits, disappearing notions more and more. Now, for example, there is this tendency to collect them not as written, not only as written information, but also as, for example, small video interviews in which therefore you want to maintain both the audio and the video and the rest. So this is the first attempt to how you represent information within the computer.
Okay, Vittore, I am not sure that the other are still alive after this full immersion in the world of computer. But if they are, they can, I don't know, make gestures, say hello, and take a break, of course. I don't know how we can...
No, now it is 20 to 1. I would say that we can have a lunch break and start again at 2 o'clock, but then it will be your turn to...
Yeah. So, folks, we had this first touch with the computer science, the basics of the computer science in this morning, and this afternoon we will deal about I will teach and speak about the digital humanities environment in a more dialogic form. So I will try to speak with you and to try to understand what you think about something in the digital humanities world. So now lunch break, take a breath, move your legs, and let's see again in this room at 2 p.m. If there are some question or problem, let us know.
But when you said 2 o'clock, because you said past something.
2 o'clock, 2 past, what I said, I don't know, 2 past...
2 past 0, because again, I think that
I would say 2 p.m.
2 p.m. Yes, no, okay. I thought that you were just because I think
I am a little bit compressed in a zip mode.
No, okay. So it is 2 o'clock. I mean 2 p.m.
Okay.
Okay.
I stopped the recording now.
Okay.